we considered this very simple problem of flipping n fair coins and then looking at the number of coins that come up heads. So let's say that x was the number of coins out of n coins that come up as heads. So this is the random variable of number of heads. And the question we asked was, what is the probability that at least 80% of all the coin flips come up heads? And we saw some bounds on this probability. We saw that Markov's inequality gives us a bound of 0.625. This was by Markov. And we saw that Chebyshev gives us 2.78 over n. Okay. So Markov basically just gave us a constant. Chebyshev actually gave us a bound that tends to 0 as n grows. But we want to find a much better bound. And as I talked about this in the last session, the idea is to apply Markov to a different random variable. And that's basically how we got Chebyshev in the first place as well. We just defined a new random variable and we applied Markov to it. So the new random variable that we said we're going to apply Markov to was e to the power of t times x. But more specifically, let me just take the expectation of this random variable. This expectation is called the moment generating function. And people usually write it like this. They write it as m sub x of t. Okay. And it shows up in a lot of different areas, but we are really interested in it just for finding the Chernoff bound. Okay, so first of all, why is this called a moment generating function? So you know what moments are, right? If I have a random variable x, the moments are basically the expected value of x, the expected value of x squared, and so on. Right? So how does this generate the moments of x? Why is it called a moment generating function? Well, it turns out if you take the derivative and if you then evaluate that derivative as at 0, it gives you the expected value. I'm just going to show you why this happens. So let's just apply a Taylor expansion to this expression here, e to the power of tx. So we get that this thing is equal to the expected value of, now the Taylor expansion of this is 1 plus tx over 1 factorial plus t squared x squared over 2 factorial plus t cubed x cubed over 3 factorial and so on. Right? And since we have linearity of expectation, I can just apply the expectation to every one of these expressions here. So this would just be 1 plus t times the expected value of x divided by 1 factorial, which is just 1, plus t2, the expected value of x2 divided by 2 factorial, and so on. Okay? So now what happens if I take the derivative with respect to t? So if I take the derivative of this function, so I'm thinking of it as a function of t, and I'm taking the derivative based on t. And let's say that I evaluate that derivative at 0. Okay? So let's just give it a name. Let's say I show it with mx1 of t. So I just define this new function as the derivative of this one. And now what is the value of this derivative at 0? Well, you just have to apply to this one. So the 1 doesn't show up. This gives us the expected value of x. Here, I don't have the t squared anymore because when I take the derivative, I have a t factor and I'm evaluating at 0. So everything from here onwards is just 0. So this one is just the expected value of x, right? And you can do the same calculation. You can see that if I take the derivative twice, then it gives me the expected value of x squared, and so on. So basically, if I have this function m, if I have the moment generating function, I can figure out all of my moments because I can just take the derivative as many times as I like and then just evaluate it at 0. Okay. Nice. Let me just erase this now. So we're really interested in this function. I want to ask you a question. What happens if I have two random variables and I take their sum? So let's say I have real valued random variables. Let's call them x and y. And just to make things easier, let's say they're independent. Okay. So what can I say about the moment generating function of x plus y? Let's just apply the definition. So this is the expected value of e to the power of t times x plus y, right? Which is the expected value of etx times ety, right? But here's the part where I want to use independence. X and y are independent. So any other function that I apply to them doesn't really affect their independence. So e to the power of tx and e to the power of ty are also independent. And if these two are independent, then their expected value, the expected value of their multiplication is just the multiplication of their expected values. So this is just the expected value of e to the tx times the expected value of e to the ty, right? And this is like the moment generating function of x times the moment generating function of y. Okay, nice. So if I have two different random variables, and if they're independent, now I know how I can find the moment generating function of their sum. And again, this contains all the moments of the sum. So it's a very handy thing. So let's actually compute this moment generating function for some simple random variables. So what is the simplest kind of random variable? I can look at maybe an indicator random variable or a 0-1 random variable. So let's say I have some variable x and it's 1 with probability p and 0 with probability 1 minus p. Okay. So what would be this moment generating function for an x like that? So x is 0 with probability p, sorry, 1 with probability p, and 0 with probability 1 minus p. Okay. So if I want to compute this moment generating function for x, it's basically the expected value of e to the power of tx, which is, well, I have a probability of p that x is 1. So that's p times e to the power of t, yeah, because x would be 1. And with probability 1 minus p, x would be 0. So this is plus 1 minus p times. So now this is e to the power of 0, but e to the power of 0 is just 1, so I don't write it. Okay. I can do some basic algebra here. Let's take the 1 out and let's factor by p. So let's say 1 plus p times e to the t minus 1. Okay. Now, there is an inequality that we use over and over in this course, and I'm going to apply it here as well. And the inequality is that 1 plus x is less than or equal to e to the power of x. Okay. And so this is my x here. So 1 plus x is less than e to the power of x. So this is less than or equal to e to the power of p times e to the t minus 1. Okay. Now, this is not necessarily a good approximation, but it actually helps us a lot later on, you'll see. So this is what I want to use. So let me just put it somewhere. Yeah, so let's say for a 0, 1 variable x, we had this. Mx of t is less than or equal to e to the power of p t minus 1. Okay, just remember that because we will later use it. Okay. What's this? Let's see what I did here. I first talked about how we can compute this moment generating function for sum of some independent random variables. And then I computed it for a 0, 1 or indicator random variable. So now if I have a sum of 0, 1 random variables, I can find this function for that sum. So that was the whole plan there. Okay, so let's do this. Let's say that I have a sum. For example, here in my main motivating problem, that's the situation that I have, right? So I have one variable x, which is the number of heads. And this is basically x1 plus x2, so on to xn, where each xi is just an indicator variable that tells me whether the ice coin flip was a head or not. Okay? So I know this function for all of these xi's, and I know that they're also independent, right? So if I want to find the moment generating function for this x, mx of t, well, this is just the product of the moment generating function for all of these. So this is product of I from 1 to n of the moment generating function of xi. But each one of these moment generating functions was at most this much. So this is at most e. Okay, let me write it completely. So I from 1 to n, e to the power of, okay, our p is just a half. So 1/2 e to the t minus. Okay. But let's keep it more general for now. Let's not put that 1/2 in. Let's say that I just had, let's say I have a different value of p, not necessarily a half. And let's say that my coins have different probabilities. So maybe, for example, this coin comes up heads with probability p1, this one with probability p2, and this one with probability pn, just to have the most general case here. Okay? So then here, I should write e to the power of pi times e to the t minus 1. Okay, but this is just the same as saying e to the power of, I just take this one as a factor out. So this is e to the t minus 1 times the sum of all the pi's. Right? But what is the sum of all the pi's? The sum of all the pi's is the expected value of x by definition. Right? So let's say I show that with mu. So let's say mu is the expected value of x. Then this whole thing would be e to the power of mu times e to the t minus 1. Okay. And well, in our case, when we were talking about fair coin tosses, so all of these p's would just be a half, and the mu would just be half of n. So this would be e to the power of half of n times this thing. Okay. Now let's actually find the bounds. And to find the bounds, I want to take this random variable here, and I want to apply Markov's inequality to it. So let's see what I want. I want the probability that the number of heads is at least 0.8 times n. Okay. So I can first multiply both sides of here by t. So I can say that this is the same as the probability that tx is more than t times 0.8 times n. Let me again do this in the more general case, and then I'll put back the 0.8n at the end. So let's say I want the probability that x is greater than or equal to some constant a. I say this is the same as the probability that tx is greater than or equal to ta. But to have this, I have to assume that t is non-negative. So I just write it here, assume that t is positive or non-negative. It doesn't really matter, everything works out. Okay. But now I want that form, so I just take the exponential function and I say this is the same as the probability that e to the power of tx is greater than or equal to e to the power of ta. Okay. Now I can apply Markov, because e to the power of tx is a non-negative value. It never gets a negative value, right? So this satisfies the requirements for Markov. And I can say that this probability is at most the expected value of e to the power of tx divided by e to the power of ta. Okay? And this is what we call a Chernoff bound. So this is like the most general case of a Chernoff bound. But here's the thing, this inequality, that this probability is at most this much, it held for every value of t that was non-negative, right? So I can basically take the minimum of this one over all values of t, and I can still say that that's a bound on this probability. So more generally, I can say that the probability that x is greater than or equal to a is at most, well, the minimum might not exist, so let's just use infimum over all values of t that are non-negative of this expression. The expected value of e to the tx divided by e to the t. But this is great because basically now we can choose our favorite value of t to give us the best possible bound that we can get. But another point that I want you to see here is that I can also do a different type of bound. So until this point, we were always looking at the probabilities that some random variable is more than some threshold. But what happens if I want the opposite? What happens if I want to bound the probability that x is less than or equal to some value a? Okay, so I can basically do the same thing, just use a negative t. So this is the same as the probability that tx is greater than or equal to ta, but this time I'm assuming that t is non-positive, right? And then from here onwards, I can do exactly the same thing. I can say this is the probability that e to the tx is greater than or equal to e to the ta. And then again, I can apply Markov, and I can say this is at most the expected value of e to the tx divided by e to the ta. Right? The only difference is that I have to use non-positive t. And I can even have the same thing that I had here. So I can say the probability that x is less than or equal to a is at most the infimum over all non-positive t's of this expression. Okay. But actually, this is not the way that we usually use Chernoff bounds, even though this is like the main idea of Chernoff bounds, and this is the classical version. The way we use them is a little bit different. Okay, let me see, what can I erase? Let me erase this part. It's basically the same as the one above. So let's say that I have some random variable x, and let's say that I show its average or its expected value by mu. Usually we want to bound the probability that x passes its expected value by some constant factor. So I usually like something like this. I want to find the probability, a bound on the probability that x is more than, let's say, some 1 plus epsilon times its average value. Okay? So it's just, instead of a fixed value of a, I want to use something like this. I want to say, what is the probability that it's a factor of epsilon larger than what I expect it to be? Okay? So I can just write this one. I can say this is at most the infimum over all non-negative t of, so I have this same thing here, but this is now my a. So the expected value of e to the tx divided by e to the t times 1 plus epsilon times mu. Okay. But now, let's say that I'm looking into variables that are like this. Let's say that my variable x is just a sum of indicator variables. And let's say that all of those indicator variables were also independent of each other, so that I can use this result here. Okay. So for this specific type of variable, now it's really important. The bound that I'm going to find now is not as general as the main Chernoff bound, because I'm applying it only to this kind of variable. So for this specific kind of variable, we know that the expected value of e to the power of tx is at most this much. This is what we computed before. So that bound tells us that it's at most this expected value, e to the power of mu times e to the t minus 1. And here I have e t1 plus epsilon okay. So I have mu both here and here. So maybe I can just take it out. And I can say this is e to e to the t minus 1 divided by e to the power of 1 plus epsilon times t, and all of it to the power of 1. Okay. Now, why did I do this? Because as you see here, I want to choose a value for t so that I get the best possible bound, right? And basically by writing it like this, I took the mu out here, and now I have to just minimize whatever is inside this parenthesis, right? And the things inside here only depend on t and epsilon. Let me see. I'm going to erase this one. I don't think I need it anymore. Okay, so I'm going to continue from here. Okay, what do you suggest I choose as my value of t? So one thing you can do is you can differentiate that and try to really find the optimal value, right? But let's just do something more intuitive. And let's just see what can I put for t so that this whole thing becomes a simpler expression. So actually, one thing I can do is maybe I want to just have e to the power of epsilon up here. So I want to get rid of this exponent in the exponent. So what I can do is just set t to be the natural logarithm of, let's say, 1 plus epsilon. Okay, and if I do this, then what I have is that the probability that x is more than 1 plus epsilon times its expectation is at most, okay, let's just put this into that. So I have e, but e to the power of t is just 1 plus epsilon, and then I have minus epsilon, so this would be e to the power of epsilon. And here I have e to the power of 1 plus epsilon times t. But e to the power of t is just 1 plus epsilon, so that's 1 plus epsilon to the power of 1 plus epsilon. And all of this to the power of mu. Okay, yeah, this looks a bit nicer. This was what I wanted to get to. Okay. And again, this holds only for random variables x that are a sum of indicator random variables, and all of those indicator random variables have to be independent. Okay. Now let's plug in our main motivating example. So I wanted to find the probability that the number of heads is more than 80% of all the coin flips. So this is just the probability that X is more than, okay, so this mu here is just 0.5 times n, right? That's what my mu is. But I want to write this part in the format of 1 plus epsilon, and I want to get 0.8. So I should write it as 1 plus 0.6. Right, so my epsilon is just 0.6. And so this probability is at most, now epsilon is 0.6, so it's e to the power of 0.6 divided by 1.6 to the power of 1.6, and all of it should be raised to the power of mu, which was just half of n. Okay. Now, this is the part where you take out a calculator or just ask Wolfram Alpha what is the value in here. And this is something like 0.859. So this is at most 0.859 to the power of n over 2. Okay. So this is the Chernoff bound that I showed you last session very hastily without actually doing the calculations, but this is how you get it. So we wanted to bound the probability that X, the number of heads, is more than 80% of all the flips. Markov gave us this bound, Chebyshev gave us this bound, and now we have the Chernoff bound, which is 0.859 to the power of n over 2. Okay, so Chebyshev already had a bound that tended to 0 as n grew, right? But now that we have Chernoff, this is a much better bound. It's decreasing exponentially, right? And this this number here in the parentheses is less than 1, so it is really an exponential decrease. But all of this process is really based on the assumption that the number here would be less than 1, right? And if we are unlucky and this number is somehow more than 1, then the bound that we get here would be awful. It would be something that is greater than 1 to the power of our expected value, which is worse than trivial. I mean, trivially, any probability is at most 1. So the only way that this approach would be useful is if I can show that this thing in the parentheses here is always less than 1. And okay, I don't want to do more calculus, but it is. So just take this expression, differentiate it based on epsilon, and find its minimum value. Sorry, find its maximum value. And you will see that, and by the way, our epsilon is always positive, right? Because I want to see what is the probability that I'm far away from my average. So assuming that epsilon is positive, just differentiate this thing, find its maximum value, and you will see that it's less than 1. Okay, or again, if you're lazy like me, just ask Wolfram Alpha to differentiate this or give you the maximum. Okay, so basically my point is that this kind of bound always works. It works for every possible epsilon. You're guaranteed that if you go through this same process, at the end here, you will get something that is less than 1, and it's raised to the power of something that depends on n. So that's good enough. Okay. And actually, some people use even more simplified cases of this. So let's give this thing inside here a name. So let's say that I call this thing, I don't know, let's call it R. So this is, the bound is R to the power of mu. Okay. So a lemma that you can, again, just prove using basic calculus, and I don't want to prove it, but I'll give it to you so that you can use it, is this. So for every epsilon that is between 0 and 1, we have this inequality. We know that R is between epsilon squared divided by 3 and epsilon squared divided by 2. Hopefully, if I don't have any errors. So if you don't want to always differentiate this for the values of epsilon that are between 0 and 1, you can just use these values for R. Again, this is just obtained by basic calculus. Just plug this in and show that it's atmospheric. Okay. So this was all I wanted to tell you about Chernoff bounds. Now I want to go to a different topic, and a topic that has less calculus in it. So let's talk about the probabilistic method. So the idea behind the probabilistic method is quite easy. Suppose that you want to show that something exists. For example, you want to show that there exists a graph that has some desired property. What you can do is to instead just show that the probability of generating such a graph is non-negative. Sorry, is greater than 0. I don't know why it said non-negative. It's greater than 0. Okay? So basically, the idea is very simple. If the probability of some event is not 0, then that event is possible. Okay? And similarly, if I take, okay, let's use epsilon for my event. If I take the expected value of some x, some random variable x, and it gives me mu, then there are cases where the value of x is at least mu. And there are cases where the value of x is at most mu. That's the whole idea behind the probabilistic method. You want to prove that something is possible, and the way that you prove it is that you define some probability space, and then you say the probability of my desired property is not 0, so it's possible. Okay? It seems like a very simple idea, but actually it can solve a lot of nice problems for us. And we've actually seen one example of this before. So the example that we saw was about 3-SAT. So you remember the randomized algorithm that we had for 3-SAT? So the idea in 3-SAT is that we have a bunch of clauses, let's say x1 or not x2 or not x3 and x4 or not x5 or x1 and so on. And so again, as before, each one of these is called a clause. And the question in 3-SAT is, can we find a valuation, a true-false valuation for our variables xi, so that the whole formula holds? The question in max 3-SAT was, can we optimize the number of clauses that are satisfied? So instead of trying to satisfy every clause, what is the maximum number of clauses that you can satisfy? And we actually saw a 7/8 approximation for this. And the idea was very simple. The idea was, suppose I just give random values to all of my variables. So for every one of my variables, I just flip a coin. With probability half, I say this variable is true. With probability half, I say it's false. Right? Then each one of my clauses will be satisfied with probability at least 7/8. Right? Because for this clause to not be satisfied, x1 has to be 0, x2 has to be 1, x3 has to be 1. So the probability is at most 1/8. Okay, and then we could just say that, let's say x is the number of satisfied clauses. Okay, this is not a great color. And then we could again just say that x can be written as a sum of indicator variables, where xi basically tells us if the ith clause is satisfied or not. And then we could say that the expected value of x is the sum of the expected value of the xi's. Right? And the expected value of each xi was at least 7/8. So this is greater than or equal to 7/8 times n. But now here's the part where we use the probabilistic method. I have a random variable, and its expected value is more than 7/8 times n. So there should be a case where this random variable gets a value that is at least the same as its expected value, or maybe even higher. Right? So there exists some valuation for these variables so that 7/8 of the clauses are satisfied. That's the idea of probabilistic method. Okay. Now, the probabilistic method is not really constructive on its own. It just can show you that something exists. Right? But we saw before how we can make this constructive for this particular case. So we had a de-randomized algorithm which would just take x1, give it a value of 0, and assuming that x1 is 0, compute the expected value of this x, which is the number of satisfied clauses, and then do the opposite. Give x1 a value of 1, and assuming that it's 1, compute this expected value, and then take the one that worked better. Right? So this is a very common de-randomization strategy. And we will see it again. So let me give you another example here. Let me see which one of these examples is easier. Okay. One of the very first problems that we saw during this randomized algorithms part of the course was the problem of min cut. But what happens if we look at max cut? So I have a graph G, and I want to divide the vertices of G into two different sets. So I have this graph G. Let's say my vertex set is V, my edge set is E. I want to divide it into two parts. Let's call this one A, and let's call this one B. And every vertex goes either into A or B. And then the size of my cut was the number of edges that go from one part to the other. Okay. So this was, let's say if this is my graph, in this case, the size of the cut is 4 because there are 4 edges going from A to B. Now in the min cut problem, I wanted to minimize this. In the max cut problem, I want to maximize. I want to find a cut that has as many edges going between the two parts as possible. Okay. Now, again, I want to use the probabilistic method here. And I want to say that there exists a cut such that at least half of the edges go between the two sides. So I want to show that in any graph G, the size of the max cut is greater than or equal to the number of edges divided by 2. Okay. again, the idea is very simple. Just define some sort of a probability space, define some process for generating A and B, and then talk about the probability that the number of edges in between is more than this much. Or talk about the expected value of the number of edges that go from A to B. Here's the simplest possible thing that I can do here. I just take every one of my vertices, and with probability half, I drop it into A. With probability half, I drop it into B. Okay? So now, let me erase this one. Okay? Let's say that I again have to define a random variable. And let's say my random variable x is just the number of edges from A to B. And it's an undirected graph, so it doesn't matter, A to B, B to A, same thing. Okay, so I can just say that this x, I always do this, I just write x as a sum of indicator variables. So for every one of my edges, let's say my edges are 1, 2 to E, I can have an indicator variable that tells me whether this edge has its endpoints on two different sides. Right? So now the expected value of x, which is the expected size of my cut, is just the sum of the expected value of these xi's, I from 1 to the number of edges. It's, yeah, I just realized that I'm using E both for expected value and number of edges, but you know which one's which. So this is expected value, this is number of edges. Okay. So, but now if I have a particular edge, what is the probability that its two sides are thrown into two different parts? That's quite easy, right? It's just half. Because you first throw one of the two sides. Let's say I had an edge from U to V. I first throw U in one of A or B. And then when I want to throw V, there is a half probability that it goes in the same place as U, and there is a half probability that it goes somewhere else. Okay? So this is greater than or equal to this sum again of just a half. So all of these expectations are at least a half. And this is just the number of edges divided by 2. Right? So what this proves to us is that if we take a random cut that was created using the random process that I explained, then the expected number of edges in that cut is going to be at least E divided by 2. So again, we can use the probabilistic method and say there is a cut that has at least these many edges in it. Okay? But again, the probabilistic method is not on its own really constructive. It doesn't tell us how to find this. It just tells us that such a case exists, such a cut exists in here. But I can apply the same de-randomization idea that I had for the previous case, for 3-sat, to this problem as well. So let's say I have A and B, and let's say I just, okay, just to make things easier, let's say that I have M edges. So instead of size of E, I just write M. And these things all become M. And let's say that I have N vertices. So I have N vertices and M edges. Okay. So just think about the de-randomization idea that we had for max 3-sat. There we took some variable and then we tried to decide, is it better to set this variable to 0 or is it better to set it to 1? Right? And the way that we guided our non-randomized algorithm was by computing the expected values. Right? So here I do the same thing. I take my first vertex and I say, is it better if I put my first vertex in A, or is it better if I put it in B? It doesn't really matter, right? So the first vertex, I just put it somewhere. Let's say I put it in A. Now I take my second vertex, right? So if I put my second vertex in A and then randomly assign all the vertices that come after this, what is the expected value of the number of edges in my cut? I compute that. Then I compute, if I put my second vertex in B, what is the expected value of the number of edges in the cut? Okay? In general, let's say that I have a bunch of vertices already there. And now I have a new vertex. So let's say this is my new vertex. And it's connected to some vertices in A and some vertices in B. And I want to decide where to put this new vertex. Now, if I put this new vertex in A, I lose this edge. This edge will be entirely in A. But I will gain these two edges, right? And for every other edge, for every edge that is not here, that has one of its endpoints in the vertices that I want to add later on, assuming that I add all the future vertices uniformly at random, the probability that I add that edge is just a half, right? So for me, just following the expected value, the best choice here is to take this vertex and put it in A. And that's our de-randomized algorithm. So for every vertex, you just look which side is better for the expected value and you put it there. But actually, in this particular case, the algorithm becomes much simpler, right? Because I'm just taking this vertex, and if it has more neighbors in B, I'm putting it into A. If it has more neighbors in A, I'm putting it into B. Right? So I don't even really need to compute the expected value. So yeah, and you can show this without even using a probabilistic argument. This would give you a cut that has at least half of the edges, right? So I'm adding my vertices one by one, and each time that I'm adding a new vertex, I'm making sure that at least half of the edges that go from this new vertex to the old vertices are going to be part of my cut. So it's easy to say that overall, I will have at least half of my edges in my cut. But again, the difference is that if you use the probabilistic method, it's kind of more, I don't know, let's say streamlined. You can apply it to all sorts of problems. We basically applied the same idea that we had for 3-sat also here, and the de-randomization is also kind of easy. So you can use this for other problems as well. Let me give you another example. Okay, I can give you the example of a dominating set in a graph. So what's a dominating set? Let's say that I again have an undirected graph G with vertex set V and edge set E. A dominating set is a subset of vertices of my graph so that every vertex is either in my dominating set or has one of its neighbors in the dominating set. So S subset of V is a dominating set if when I take S and I take all the neighbors of S, I use this to show the neighbors of S, then I have all of my vertices. Okay. So for example, let's say I have this graph. So I basically want to choose a bunch of vertices so that every other vertex is a neighbor, right? Maybe I can choose this one and this one, right? If I choose these two vertices, then every other vertex has at least one neighbor that was chosen. So this is a dominating set. And I think we don't have a dominating set of size 1 here. It's kind of clear. So this is the smallest possible dominating set for this graph. Now, of course, in any given graph, you can just take all the vertices and say, this is my dominating set. So every graph has a dominating set. But of course, we want to choose as few vertices as possible. So the problem is to basically do like minimum dominating set. Now, this problem is actually NP-hard. So we don't expect you to find a polynomial time algorithm for this. But here's the result. And again, like one of the cases before, when I write the result, it might not really seem intuitive. But when you see how I obtain it, you'll see that actually it is quite easy. So let's say that I have a graph G. And let's say that the degree of every vertex is at least delta. So I want to say that for every vertex V, the degree of V is at least delta. Okay, so the lemma that I want to prove is that there is a dominating set S such that the number of vertices in the dominating set is at most this much, n times 1 plus log of 1 plus delta divided by delta plus 1. Okay, this is what I want to prove. But again, as I said before, whenever in computer science you see things that are not very intuitive, that's because they first apply the tool and see what they can get, and then they put it back into the theorem or the lemma. So don't be worried about this. So I want to say that there is a dominating set of some size that is smaller than some size. What can I do? I want to use the probabilistic method. So I can just come up with some probabilistic process that gives me a dominating set. And then I can talk about the size of that dominating set on average. I can talk about the expected size of the dominating set that I get out of my very random process, right? And then I can use the probabilistic method and say that there is a dominating set whose size is less than or equal to the expectation. So how would you randomly choose a dominating set? Yeah, but we don't want to do things like that. We want to really just leave everything to chance. So I can say that I take every vertex by just a coin flip. So let's say I take every vertex with probability half. Or I don't necessarily need to have a fair coin. So let's say I take every vertex with probability P. Okay? But my problem is that if I just flip coins for every one of these vertices and I take each one of the vertices with probability P, I might not get a dominating set. So I have to make sure that my process always gives me a dominating set. Otherwise, the expected value of the size of my set doesn't tell me anything, right? So if I just give you like a random subset of a graph, how would you turn it into a dominating set? Well, if I give you a random subset, for example, let's say, okay, it's this one. Let's say I flipped my coins and the vertices that were selected were this one and this one, right? And unfortunately, I see that it wasn't a dominating set. But I can just say, okay, I know that in any graph, if I take all of my vertices, that's a dominating set. So here, some vertices are already dominated in the sense that they're either in my set or they have a neighbor in my set. So I don't have a problem with this vertex, with this one, this one, this one, and this one. These vertices are all dominated. Any vertex that is not dominated, any vertex that is not in my set and has no neighbor in my set, I just say I add that one to my set as well. Okay? So to be a bit more formal, I say that I break my set S into two parts, S1 and S2. Okay? And S1 is chosen using that probabilistic process. This is random. So this is just take every vertex with probability P. And again, I'm just saying P because I want to be sneaky and later on find the best possible value for P. Now, how about S2? Well, S2 is basically just, if I want to write it formally, it's the set of vertices such that, well, they're not in S1. So V is not in S1. And they don't have a neighbor in S1. So neighbor of V intersection with S1 is also it. So I first choose my S1 using randomization, and then based on S1, S2 is very well defined. It's just the set of vertices that were not dominated. And then I just say that S is the union of the two sets. So now I want to compute what? I want to compute the expected size of S. So what is the expected size of S? Do you agree that this is just the expected size of S1 plus the expected size of S2? Because S1 and S2 are always disjoint by definition. So this is just the expected size of S1 plus the expected size of S2. Okay, so now let's find bounds for the sizes of these two sets, S1 and S2. What is the expected size of S1? Again, this is a random variable. So as usual, I'm just going to write it as a sum of some indicator random variables. So let's call those random variables S11, S12 to S1n. And S1i is an indicator random variable that tells me whether the ith vertex was chosen to be part of S1 or not. Okay, so what is the expectation of S1i? So I said I choose every one of my vertices with the same probability P. So the expectation of S1i is just P. So what is the expected size of S1? It's just the sum of the expectation for all of these, so it's just NP. So the expected size of S1 would just be NP. So I have n vertices and each one of them came with probability. Okay, how about S2? I can again do the same thing, right? So I can say that the size of S2 is the sum of a bunch of indicator variables, S21, S22, so on to S2n. And again, S2i is the indicator variable that tells me whether the ith vertex is in S2 or not. Okay. Now, what is the expected value of S2i? The expected value of S2i is basically the probability that the ith vertex gets added to S2. Okay, but let's look at that. So let's say this is my vertex I, and it has a bunch of neighbors. So let's call those neighbors, I don't know, U1, U2 to maybe UK. Okay. So in order for I to be added to S2, it had to be undominated by S1. So I couldn't put I into S1, and I couldn't put any of its neighbors into S1. What is the probability that none of them are in S1? So the probability that I is not in S1 is 1 minus P. The probability that U1 is not in S1 is 1 minus P. And it's basically 1 minus P for all of them. Right? So the probability that none of these vertices are in S1, which forces I to be in S2, is at most 1 minus P to the power of K plus 1, because we have K neighbors and I itself also counts. So this is at most 1 minus P to the power of K plus 1. But K was the degree of the vertex I, and I assume that every vertex has degree at least delta. So instead of K plus 1, I can just write delta plus 1. So that I have the same bound for every vertex instead of having a bound that depends on the degree of the vertex. Okay, so I know that the expected value of each one of these indicator variables is at most this much. So the expected value of their sum is just n times this. So the expected value of S2, the expected value of the size of S2, the expected size of S2 is at most n times 1 minus P delta plus 1. Okay. Some more calculus again. Let me see if I have it. I don't really want to do it, but okay. So the expected size of S is just going to be this one plus this one, which is like I just factor n out. So it's n times P plus 1 minus P to the power of delta plus 1. Okay. I want to get rid of this 1 minus P. So again, let's say that I use the idea that 1 minus P is at most e to the power of minus P. So I can say that this is at most n times P plus e to the minus P delta plus 1. Okay. Now this is kind of easier to differentiate. Yeah, instead of doing all the calculus, I'm just going to tell you what we plug in for P to get a good bound here. So again, the idea is that I took this part, which only depended on n, and I have this part, which depends on P and delta. And I want to find the best possible value of P, right? Because I want this to be as small as possible. So I want the value of P that minimizes this. Again, I can just use some calculus, but in order to get this particular result here, you can just set P to be the log of delta plus 1 divided by delta plus 1. And if you do this, and if you plug this particular value of P, and of course, P is a probability, so it has to be between 0 and 1, and it is between 0 and 1, the way that we defined it here. So if you just take this value of P and you put it into the inequality that we had here, you get that the expected value is at most this. the thing that was originally in the lemma. And so if my expected value is this, then there should be a set that has a size that is smaller than or equal to the expected value. And so this is the part where we're applying the probabilistic method and saying that there is a dominating set S such that the size of S is at most this much. Okay. So just to repeat this, the idea is that you want to show that there is some object that satisfies some property. For example, there is some object, in this case, a dominating set, that has a size that is at most this much. What you do in order to prove that is that you define some probabilistic process, some randomized process. And your randomized process should generate objects of this type. But then you go back and analyze it and say, what is the expected size of the object that was generated by my randomized process? And you can always say that there is an object whose size is less than or equal to the expected size, and there is an object whose size is greater than or equal to the expected size. Okay? Now, let me see if I can try another example. I'm not completely sure if we have enough time, but let's do it anyway. I can give you another example that is also a graph problem. And that's the example of Ramsey numbers. So let's say that I have a complete graph on n vertices. So I consider the graph Kn, and I color each one of its edges with one of two colors, either red or blue. So for example, I can have K3, which is just a triangle, and I just color every one of the edges either red or blue. Okay? So a problem you might have seen is that if I take a graph with 6 vertices, if I take K6 and I color its edges like that, no matter how I do the coloring, there will either be a blue triangle or a red triangle, right? And that's actually quite easy to prove. So let's say I have 6 vertices. I just take vertex 1 here, 2, 3, 4, 5, and 6. Between any pair of vertices, I should have either a red edge or a blue edge. Okay? So there are 5 edges going out of 1. So 3 of them have to be the same color. Let's say those 3 are blue. So let's say I have blue edges like this. Now I take these 3 vertices. Either there is a blue edge going from one of them to the other, in which case I have a blue triangle, or all of the edges between these 3 vertices are red, in which case I have a red triangle between these 3 vertices. So if I have a graph K6 and I color the edges with 2 colors, I will either get a K3 of one color or a K3 of the other color. And basically, this is how we define Ramsey numbers. So the Ramsey number of RB is the smallest n, such that if you take a complete graph on n vertices and color it with 2 colors, then you will either have R vertices such that all the edges between them are red, or you will have B vertices such that all the edges between them are blue. Okay? And actually what I showed here was that the Ramsey number for 3, 3 is at most 6. Right? And actually this is exactly 6. You can see that it wouldn't work with 5 vertices. You can